all, I would like to thank Indian Academy of Sciences for this opportunity to speak here. So I will try to keep my talk as basic as possible. Okay, so I'll try to explain the issue that that we do. So suppose I have a cylinder. So this is a general issue that I'm trying to address. And in general, engineers, physicists, other scientists, they do several problems on long cylinders. So what do we mean by long cylinder? Let's say we are in 3 dimension and the length is parameterized by L, and I have a domain omega L, which is -1 times L cross B01. So L is the length of this cylinder, which I have written here 2L, you can see. And I have, so this is the first dimension. And this is the, let's say this is an R2B01, which is a circle. So this is our usual cylinder. And this B01 set, I may call it as a cross section. In general, if I say it a cross section, then you understand, it is understood that it's a circle. Okay. So the issue that engineers and other physicists always encounters many times is that they have their they solve problems for their purposes on long cylinders. But in general, computing on higher dimension is generally a difficult question, because suppose they have a PD on this cylinder omega L, which has length 2L and which is large, let's say very large. Okay. Now the question, the difficulty that they generally face is that computing, finding solution to a given PD. So whatever the PD may be in their hand, finding explicit solution may or may not be possible. If it is possible, good. But in most of the case, explicit expression closed form solutions are not available. So in that case, what they have to do? They have to discretize the problem and go to numerical methods. And while going to numerical methods, one of the biggest challenges that they face is computing integrals. I mean, when they discretize the domain, computing integrals may take a long time, even in very good computers, supercomputers. And this difficulty significantly enhances when you go from a lower dimension to a higher dimension. For example, computing an integral via a numerical method in 2 dimension, the same integral in higher dimension, in 3 dimension, the efficiency, I mean the time taken and the computational cost becomes very high. And this is called, this is one of the major difficulties that engineers, physicists, everybody faces, and this is called curse of dimension, this problem. So what they do generally, in many cases, if a certain differential equation is given to them on a cylindrical domain which looks like this, what they will do in most of the time, they will put the same problem, instead of doing on this 3-dimensional cylinder, they will solve it on the 2-dimensional ball. So instead of solving on the whole rectangle, they will just solve on this cross section, because this cross section is of dimension 2, and probably they will be able to do the whole computation there. So suppose I have this PD, some PD L can be a Laplace equation, heat equation, wave equation, whatever PD is written now, it's general PD. So UL is the solution which depends on the length of the solution, which is hard to compute. So instead, what they will do, engineers and physicists, they will solve this problem, L of U infinity, on this ball in this 2-dimensional set. And they will extend this U infinity to the whole cylinder. So they will extend it as the function of x2, x3. So if this cylinder is in 3 dimension, x1, x2, x3, so they will just drop this x1 term. They will extend this U infinity, they will compute this U infinity and extend it to the full cylinder. Well, and they will go on with the computation most of the time. Now, the question that arises, there is a significant risk of doing it, simplifying your problem in hand. So there should be some mathematical, they seek for mathematical justification. Why, some kind of mathematical justification why such a thing can be done. In general, if you take this function u infinity, two-dimensional functional, so which is the solution of the same PD, you see the same L over in these two places. This problem is in 3 dimension, this problem is in 2 dimension, which is easy to compute. So if you put the same function in the whole cylinder in 3 dimensions, it may not be a solution. So it needs some justification to say why they can do so. And from this, the whole thing starts actually. So this is the issue that we. These are the kind of problems I will try to address. That whether I put a PD on a long cylindrical domain, whether I can whether this solution UL has some connection with the same problem that is put on a lower dimensional, in particular the cross section of the cylinder, the solution that you get for a lower dimensional problem. Okay, now from mathematical point of view, the things can be generalized, and we can talk of more general cylinder of the form L times U1 cross omega. So this is the cross section. Omega is a bounded set, smooth bounded set. U is a subset of Rm. Omega is a subset of Rp. So things are in more general dimension that we study as a mathematicians. And for example, this U is 1, 1, minus 1, 1, and omega is small omega is minus 1. Then you guys get usual rectangle in 2 dimensions. And I said if this U is minus 1, 1, then as I drawn up, and this omega is the ball, you can see it's the ball. It's the usual cylinder that you get. Things can be more general cylinder. If this U is 1 dimensional, if this U is 2 dimensional ball, whereas the cross section is 1 dimensional minus 1, 1, then you are actually looking at domains like this that becomes bigger and bigger. So it's like a coin of height, and the coin kind of becomes flat and flat. So those kind of domains are always are also we take into account. Okay, so just wanted to convince you that the problem. The problem that was first studied in this direction, it was due to my supervisor Michel Schiffer from University of Zurich. I think it was. I think Professor Schiffer told me directly, or maybe a colleague of him, that people from CERN in Geneva, they came to him explaining what I said in the beginning of my lecture, that they have some problem, complex problem of something. Doing something in a long cylinder, they do something in a long cylinder, and they use this approximation in 2-dimensional approximation, and they use that solution U infinity. They compute a lower dimension solution to compute this higher dimension thing, but they have no justification. So they said, and they asked him that is there any mathematical justification so that we can go on? So we have some confidence while going on with those experiments. So as a mathematician, my advisor, they started with more simplified models of mathematical models, not the exact thing which they have probably, which gave him, which he got from the scientists. So they started with this problem, minus Laplace and UL, the simplest PD and probably the most useful PD, UL equal to F, and UL is 0 on the boundary. So Laplace equation set on this omega L. Remember, this is a cylinder. Let's say, think of it as a three-dimensional cylinder, the usual cylinder that I drew in the beginning. And then there is the problem of the same. See, the Laplace, the same equation is the same Laplace equation that I put on the cross section. So it's the same equation, but in a lower dimension. And let's call U infinity is the solution. That is in the lower dimensional cross section on the ball. Now, what is the relation between this UL and what is this U infinity? So engineers will use this U infinity, but obviously this UL is not identical equal to infinity. That cannot be the case, because then this boundary condition will not be satisfied. But is there any other relation? That's the question. So what they answered, I think it's back in 1999 or in the early 20s, 2000. What they showed is that in a series of paper by Shippo, Rogier, and Yersian, that the solution UL is connected to the solution U infinity. The solution is a lower dimension solution via this fact. So this is a norm. This is a norm, semi-norm on the appropriate space where you find the solution for these equations, and in this norm they are close enough. So that fact was being established, but the compensation is that instead of getting the solution on the whole cylinder, you see that I have replaced here omega L by 2. This approximation is only in the middle of the cylinder, and the rate that they get is in the initially they produced polynomial rate of convergence. So as L goes to infinity, this thing right hand side goes to 0, right? So UL becomes closer and closer to infinity in the gradient norm, and the rate of convergence is exponential. So that justifies that what engineers were doing. Probably that was a different problem that they're doing. That doesn't justify, this problem doesn't justify that their problem they can do it, but there is connections in some problems. So that was the first thing that was being done. Okay, then several papers were and several articles being written on several problems. Like for example, an important equation is Navier-Stokes equation. Navier-Stokes equation also satisfies this property that if you set Navier-Stokes equation in a long cylinder and then you let that L goes to infinity, you make your cylinder long and long, then the solution has some connection with the same problem set on the lower dimensional problem. Okay. Now the result that we did was a variational problem. So I spoke about this problem in the beginning, and then the solution has one more characterization. Is the fact that the solution is a minimizer of some energy functional, some kinetic and potential energy. So which is given by this form. Okay, and this space you can neglect about it. This is the appropriate space where you find the minimizer. So it becomes a variational problem. The question is that the generalization that we looked at is that look whether we can replace this J of UL by a more general functional instead of this nonlinearity, smooth nonlinearity, fx equal to x square by 2. Mod x square by 2, if you replace it by a general strictly convex function f of grad u, this f might not have any differentiability. So so what do we lose? We lose the solution UL to this problem. The solution UL to this minimization problem may not have any equation. I mean, it may not be the solution of any Euler-Lagrange solution of some equation. In this case, you see the same UL has two properties. It satisfies this equation. It is also the minimizer of a variational problem. So these are two equivalent things. If this nonlinearity is like mod x square by 2, one hand it is a variational problem, other hand it is a solution of this Laplace equation. But when you generalize, when you make it purely a variational problem, one may not get this equational structure back. So it's a pure variational problem, and we found out that in this case also, the solution on the long cylinder is actually connected to the solution on the lower dimensional solution U infinity. U infinity is in, you can see here, it's in H01 of small omega, which is the cross section that I started in the beginning. So this was one of the results that we did, and the next result in this direction was so you see here there is a fraction. This is a fractional Laplacian operator. So in previously there was no S, it was only Laplacian. So now this is a fractional Laplacian operator. So this operator models the path of a movement of, let's say, $1 bill. For example, I have a $1 bill and it goes to somebody. It moves to, let's say, China first, and then it goes to US. Then it stays in US for a long time because it's dollar. It's been used by local people. Then suddenly it goes to India back again. So the path of an $1 bill, the movement of the path of an on-Euler bill is modeled by something called long jump process, censored long jump process, and that gives rise to fractional heat equation, and that's how fractional this operator comes into picture. So we'll and the explicit definition is here. So we looked at this problem. So if you look at the fractional Laplace problem on a cylinder, whether this problem has the connection with the lower dimension problem or not. It was seen that it is the case again for S between half to 1, that it is again connected to this lower dimensional problem. Now, now the next problem, but this may not be the case. May not be always the case that every PD that you insert in a long cylinder, as you let the length of the cylinder goes to infinity, it will have connection with the corresponding problem in the cross section. For example, this is one of the problem, and probably the only problem till date which has this feature. So the problem is an eigenvalue problem. So if you put A equal to identity here, you get back Laplacian. So it's a elliptic positive definite operator matrix, and but the trick is the boundary condition. You put one puts a zero boundary condition on the lateral boundary on this part, and on this boundary one puts a Neumann boundary condition. So on the condition on the derivative of the function. So if someone does that and try to analyze the solutions, the behavior of the eigenvalues, then we showed that it becomes independent of the problem of the cross section. So that's a surprising result that we got. And so there are several other papers, like I said, Navier-Stokes, variation inequalities, elliptic parabolic problems. A lot of work has been done testing this fact that whether a given equation, as the length of the cylinder goes to infinity, whether it has a connection with the lower dimension problem or not. Several authors like Michel Schippo, Roger Elker, Yersian, Del Pino, several other people has worked on this issue. And I want to finish with one small video. So I was talking about the sun. If you see this video, they have these long tubes in CERN that where they find this Higgs particle. They send rays through long tubes, and the particle collides to form these boson particles. So I mean, this was just a practical example where you at least see these long cylinders into pictures. And lastly, I'll just end up with some references. These are some of the works that we did. And finally, thank you for your participation.
Thank you, Prosenjit. We have one question from Dr. Rakesh Kumar Mishra. What is difficulty of cylindrical model equation? What is easy to predict through model? What is used in engineering or applied sciences?
In general, as I said, once you have an equation in a cylindrical domain, it may not be a closed form solution, may not be available. I mean, it's one cannot write down what UL explicitly looks like, because the function on the right hand side is maybe an unknown function, and if it's very hard to, most of the cases not possible to do. So, but we have to work with. They have to work with this solution. They have to know for some reason the behavior. So, so this is the hard part, that you do not know what it is, but you have to work with it. So what you do some approximation, right? That is always the case. We cannot tackle the hard problem. You find a method of approximating. Whether that approximation is correct or not, that's a different analysis to it. That's a different question. Whether your method of approximation is correct or not, that's a completely different question. Whether you are doing it, that's a error analysis. That's a different kind of thing. Okay, but that's a similar kind of thing here. I mean, and it's surprising in the beginning that one may not see this connection, but this connection lies in at least the equations that I showed. That in many equations that it's case, especially in linear, non-linear, no result. Still now no results are available. But even in linear, like an eigenvalue problem that I showed, it's a linear equation, but still you may lose that connection. So It depends on problem to problem, the problem in hand.
Sure.
I
Yeah,
hope
can-
that answers.
Yes, go ahead, please. Yeah, I can see that it can be useful in some of the numerical simulations in physics as well.
Yes. Because once you go in a lower dimension, you can compute. I mean, computing in a
easier
lower
to-
dimension is
That's
much easier. And in reality, it has a connection. I mean, if there was no connection in reality, it would not work. But since it has a connection in reality, so it works. So there's a...
Okay. Let me just check, Prosenjit, if there are more questions here. Someone is commenting, Rakesh is commenting, it's used in LCH. I'm not so sure. Okay, large collider head, maybe.
Okay. Yes.
And he appreciated your answer. Okay. So thank you. We are.